Hello, I'd like to talk about Jeffrey Hinton's second paper on capsule networks today. Basically, in the first paper, they introduced capsules in the sense that capsules is just a bundle of new ones. So each capsule will have a vector input and a vector output. By convention, we will say the early layer is the child capsule layer, and then the next layer will be the parent capsule layer. So in the child capsule, let's say in this child capsule layer, this first child, we have like U1 input and U2 input and so on. And in this parent capsule layer, let's say we have output V1 and V2. In the first paper, this U1, U2, and so on input to this child capsule layer will first be transformed to the perspective of this parent capsule. More precisely, if I have let's say a UI here and kind of connecting to a J parent capsule, and let's say I have output VJ here. This UI will first multiply by a transform matrix Wij, and then like the similarity, or like how does this UI agree with this Vj, will be just simply computing the inner product between this Uij UI and this Vj here. And in a nutshell, if this inner product is larger, then the weight here from capsule I to capsule J will be bigger. And in this second paper, basically instead of having just one U, it split the U in the first paper into a dedicated post matrix M, and also a activation value, like just a scalar value. And similarly for V, also have a post matrix and also a activation value. And in this EM paper, the post matrix is simply a 4x4 matrix. I guess the rationale is, if we consider the three-dimensional space, a 4x4 matrix is sufficient to capture all the transform matrix. And then similar to the first paper, the post matrix, let's say if I have, for capsule I here, I have, let's say MI, input MI, and activation AI. This post will be first transformed from the child perspective to the parent perspective. So let's say if like I have a parent capsule J here, this MI will first multiply by Wij to get something we call it Vij. And from this Vij, we determine currently if the child capsule I actually agree with the parent capsule J or not. More precisely, for a post H, the agreement of the post is gauged by a cost function like cos I, J, and H. That's basically from capsule I to capsule J. And it's just equal to minus log an estimated probability that's approximated with a Gaussian distribution, with mean and variances are actually approximated using EM that will be explained later on, and taking value that's the adjusted post under the parent perspective for the H element of that post matrix. And also for the EM estimation, the assignment probability from capsule I to capsule J will be calculated. That will be Rij here, but that will be immediately scaled by also the activation of the capsule I. that is like Rij, therefore will be replaced by AI multiplied by Rij. And finally, Aj will be computed as the sigmoid function of the weighted sum of all the costs weighted by Rij and offset by a value Bj, a bias Bj here, and then multiplied by a parameter lambda. And the lambda here is a inverse temperature parameter, similar to simulated annealing, that basically will have a high temperature to begin with and slowly decrease the temperature. In other words, we will have a small lambda and gradually increase lambda as we have a better and better estimate of Rij.